agent is how we can define rationality, so the ability of understanding some goals and trying to maximize the actions so that you get as close to the goal as possible. And given that notion of rationality, we defined the state space representation, which is a common format in which you can represent problems on a certain level of abstraction. And this level of abstraction is helping you very much to solve the problem on the right level of complexity. So the advantage of having this common representation for these problems in the state space representations is that we can now look at generic solution, so generic algorithms to solve all the problems that fall in these categories and then that can be represented as state spaces. So I want to go back a bit to the notion of search spaces, state space representations, so that we really understand how this can work and how we then get a generic representation on which then the second part of the lecture focuses, namely on how can we find in these representations the solution as quickly as possible. So yesterday we looked at search methods for agent actions. We formulated goals and problems. So now let's see how we do that in practice in a specific problem that you want to address. And the problem that you want to address is that you have two jars. One where there's room for 5 liters, one where there's room for 3 liters. And you can fill up the jars to the full, both of them. And you can pour the water from one of the jars to the other one. And the goal is to have a 1 liter in one of the jars. So now we can, of course, start thinking how we would solve that. We'll do that later. But first, let's think about how can we represent this as a state space representation. So how can we describe how a situation is and how a situation changes according to actions that we can take. So take a couple of minutes, try to understand the problem. So there is the graphic. You start from some empty situation where no water is in the jars, and you want to achieve the situation where you have 1 liter in one of the jars and these different actions. So think about how you could represent this as a mathematical abstraction, a state space representation in which you could then later apply this idea of what are the possible actions that I can take and how can I formulate them, again, in some abstracted way, like we did with the travel through Romania yesterday in the lecture. So think of it. So how could a state, what does a state look like? What information does it need to contain? Anybody? Shout. Liters of water. So, but that is not, it's half of the answer. So liters of water of what? In jar, yes, but in 2 jars. So we have 2 jars. Yeah, so we have the left one and we have the right one, and we want to represent that there's water in the jars. So basically, a state looks like, I write it here because then it's on the camera. So if that doesn't work, tell me. So we have 1 natural number which gives us the liters of the left-hand jar, and 1 that gives us the liters of the right-hand jar. So that is a mathematical representation of the state where I have water in one of the jars and water in another one, and the x and y gives us the number of liters, as you said. Yeah? I will just do it like this. So we have an x, y representation for a state. So what is the initial state? What is the starting point as described in this slide? 0, 0. Exactly. That's the starting state. What is the goal state? How can you shout a bit more?
0, 1 or 1,
0, 1, 1, 0. Very good. So that's the root. So let's start. Goal. 0, 1, and 1, 0. Do we have more? More goal states? Yeah? That's it. Yes, you can say that. So that would be an abbreviation, I would say, for 0, 1, 2, 1, 3, 1, and so forth. Because all of them are also goal states. So the only question I have asked is, can I have 1 liter in one of the jars? It doesn't say anything about how many liters in the others are. So we have many of those goal states, and we can abbreviate them with the variable x1. Yeah? So what are now the transitions? What are the actions that I can take? And how would you write them down in a mathematical way? So let's take the description here. You can fill a jar with fresh water. Yeah? Sorry?
X plus 5.
Almost. I wouldn't say that the jar only fits 5 liters. So if you put 5 liters, then the X amount that's already in there sort of pours outside. So I think the situation is if you fill the left-hand one, so let's call it L, it's an action L, then you get from a state xy to a state, the left-hand one, what would be the result? Exactly, 5y. Yeah? More actions, what else can I do? Yeah? Okay, so now, so I think there is an easier one. Let's do the easier one first, and that is fill the right one. Yeah? So we have an action R, and that is we have an X, Y situation, and what we want to get into is a situation what? Exactly. Yeah? So basically now what we've done is we have defined states. So that is just all the pairs x and y with natural numbers, the number of liters that we can have in the jar. Then we have a start space, which is empty on both sides. And then we have a goal states where one of the values is a 1, or both, doesn't matter. And then we have these transitions. Yeah? And now what we can do with this information that we have is that we systematically looked. Oh, sorry, I forgot your solution, that your action that we can also take, the important one, the most important one, and that is to pour water, the content of this, into this. Yeah. So this was the 5 liter one, and this is the 3 liter one. And now it's a bit complicated to write it up, so there's no magic, but it means that if you have x and x is bigger than 3, then this will always end up with a 3, and otherwise it will end up with y plus the content of x. Yeah? So you take the maximum of 3 and, the minimum of 3 and x plus y. Yeah? So that would be an action pouring from right to left. And I think what I just said was this one is empty at the end. Oh no, it's not empty. It is if y is already filled, then you keep the remaining of x in the big pot. So in other words, if I have 4 liters and 2 liters, then I can pour 1 liter in here, and I will end up with 3 and 3. Yeah? That would be the pouring action right to left. So if we now get to the real problem that we start out with 2 zeros, And there is another one, of course, you can also go from the left to the right. So we start with 0. What are our options?
Either require the water in the 3 liters one or the 5 liters one.
Okay, so we can take the action L, we fill the left one, or we take the action right. Fill the left one, fill the right one with full water. What is the state we get into? 5-0. What is the action of the right pouring? If you fill the right one, 0-3. So now, if we are in this situation, what are the actions that we can take? Meaningful actions. So which of the actions is that of the ones that I gave here? From left to right. Yeah? So we do LR, so we pour from left to right. That gives us that there remain 2 liters in this one and 3 in the new one. Yeah? Any other option I have?
Just R.
Just R. Exactly. And then I end up with 5, 3. And here it's the other way around. I can use RL, pour the right to the left, and I can fill the left one. And obviously from this situation, I can go on. And if you apply this structurally, systematically, you will end up with the situation where you have, in one of the jars, you have only one. Yeah? So what we've done is now to encode a standard daily life problem, filling water in jars, into a mathematical state space representation, write it down as a state space of the entire options that I have in order to act on my jars. And I can now just look through this systematic tree that I've built here to find a path from the empty via some actions to the situation that where the goals hold. And that's the whole idea of this state space representation and search paradigm, that we need some kind of abstract representation of our problem. And once we have that abstract representation of the problem in terms of a tree or a graph, we can simply search. And how you search efficiently, that's what we're going to do in the rest of this lecture. Before we do that, I want you to go back to this Schnapsen-like game. But there's a question here. Yeah.
Is there another action? The actual emptying jar?
Yes, fair enough. Yeah. So the question was whether there wasn't an additional action that you can take, and so you can simply also empty a jar if it's full. So that would be an action empty left and empty right. So you would have 2 more actions, and you would have to take them into account. And the interesting thing is if you would now apply the empty left action on this, you would go back to the beginning. So that's why I said it's not necessarily a tree, but it can also be a graph where you go back to the root. Yeah? But this is right, so I've forgotten 2 more. So empty left and empty right. I've forgotten those. So now let's look at a very, very simple card game. It's not even a card game, it's simply a sort of a shadow of a card game. You have 5 cards on your hand, just 1 player, single player game, full information. You have these 5 cards, and you want to play them so that you get to more than 20 points as quickly as possible. So for a human, this is sort of very easy. You play the highest cards first and you're done. Yeah? But how is a computer supposed to know what it has to do, and that it has to start with the ace before the 10? Yeah? So here is a mathematical representation of the problem. So you have 1 hand of 5 cards. You have a player P, and it has a representation of the cards. So this would probably be a vector, so an array of 5 values, and each of the values could be one of the 20 cards that you have in the game. And you start out with a random distribution, so your goal distribution, your start point, your root of your search is a random card game. And then you have actions that you can take. And the actions that you can take is play card number 1, play card number 2, play card number 3, play card number 4, and 5. The game succeeds if you have collected more than 40 points, so you need some kind of measuring the goal, which is just counting the cards that you have played on the table. And so it really is extremely simple. And this is then the state space representation. I use now images of cards, but usually you would use mathematical numbers between 1 and 20, and you have certain properties. And basically what you see here is that there was some animation, yes. If I play the ace of spade, no, this is not spade. What is the English word for? Sorry. Oh yeah, club. Yeah, the ace of club is the first card I could play. The jack of club, the queen of club, and so forth. These are the 5 options that I have. And you see them back in the 5 states that I can get into with the value, the utility value of each of those, namely, when I play an ace, you get 11 points. When I play a 10, you get 10 points. So that is the V value here. So we have now a state space representation, which eventually ends up in a goal here. If you play the ace first and then the ace first here, you end up with 22 points, which is very simple for humans, but we want a generic algorithm that finds this as quickly as possible. So now I have some questions, and I have a Menti for that, again, a Mentimeter. So if you would go to this page. The question is, if we have this game now, 5 cards, you play 1 card, then the question is, how many states do you need to maximally investigate to check for all possible solutions? Is it 16, 1024, 54,321, or is it 120? Okay, so this is nice. Let's start with the 1024. So would anybody want to explain why it is 1024? There are 50 people in the room who think this is the right answer. So one of you should explain this to me, please. Okay, what about the 21 people who thought it was 120? Yeah?
We like 5 factorial because the first round you have 5 options and the second round 4 options.
Okay, so the answer was, I don't know whether you understood it in the back, that it would be the factorial, namely in the first round you have 5 options, in the second round you have 4 options, in the third one you have 3, in the fourth one 2, and then just 1 card you could play. So who's going to explain why you have 1024? Yeah?
I also did the 5 factorial, but that's just for 1 file of the cards. Then for the other card, there will be another line of thought that will go for factorial. Then I just kind of estimated that if you
Okay, so the argument here was that there is also some other set of cards, which I don't know where they come from, but that would multiply the factorial idea by some factor, and this one seemed to be a bit high, and this one was therefore taken as the answer. So, to be honest, this is the right answer, because I don't know where these other cards would come from. This is the nature of the game, that it's very simple. It has only the 5 cards. You play one of them, and after having played one of them, you only have a choice of 4. But for all the 5 cards you've played already, 5 options that you've played, you have these 4. So it's 5 times 4 times 3 times 2 times 1. Okay, so there's the next Menti to come. And that is, what is the property that makes this possible so that this is so small? There's a specific property, and the answer, number 1, is the size of the states increase per level. The second one is the number of transition decreases per level. The third one is the number of transition increases per level. And the fourth one is the size of the states decreases per level. Okay, let's show the results. Okay, and this time the majority is right, because of the fact that we are not taking cards back from some pile. The number of possible transitions, so the choices we have of each of the state, they reduce. So the set of choices we have becomes smaller every time we make an action. First, we have 5 cards we can choose from. Once we have chosen, we only have 4 left, and so forth. So what would be now the maximum number if the number of actions would remain the same? So if we would have a pile of cards where we would be able to choose one new card, and we would play the same game. But now, it's with taking cards from the pile. What are the options? Is it 100,000? Is it still 120? Is it 3,125, or is it 14,400? That's right. So we still have 5. Sorry, that's a very good question. So we still have only 5 cards that we are playing. As the answer space is finite, and we have the boundary of 20, you wouldn't run infinitely often, but there might be a case where you have 2s and 2s and 2s, where you only have 2s, or what is it, the smallest number. So it's a good question. Let's just consider a tree of length 5, so 5 actions we take. What's the maximum number? Okay, anybody ventures a guess? Tries to explain. Why? That was the perfect answer. So if you always get a card back, you have 5 choices in the first round, 5 choices in the second, 5 in the third. So it is 5 times 5 times 5 times 5. So it's 5 to the power of the depth of the tree. And I'll see how many of you had that intuition as well. So that is quite what the majority also thought. So we get back to this later. Let's see. So that is still, with this very simple game, is very easy to calculate, because we are talking thousands of moves, but a move is milliseconds nowadays if you implement these search algorithms. So that is still to be done. If we think of the real game of Schnapsen, where you have still only 5 cards on your hand, but the uncertainty of the other 14 cards, there are 14 cards left that are uncertain, you have the chance that you have to look at so many different combinations that we are talking about billions of nodes that you would have to investigate. So now we come really to something, even if you have a simple game like Schnapsen, you really become into search trees that are very, very difficult to deal with. So now the question is, how can we now look at decision making, namely finding the right set of actions, the right sequence of actions to get from the root to one of the goal states by search? And this is a relatively simple set of algorithms that you're going to see, but they are very important in computer science and in AI. So we take the time to go through them really one by one. Nothing is shocking, I think. If you think about it, it's all relatively clear. What you basically do is we have the state representation that we've just seen with the jugs and with the game. And we now build something else, namely a data structure that's called a search tree. And we start with the search tree with the state, the initial state that we are in. So this initial state is called the root of the tree, because now we really want to build a tree. And that basically means we have one starting point, and these starting point might have leaves or might have successors, but you can never go back to the starting point. That makes it a tree as opposed to a graph. So the goal states are somehow in this tree, and we want to find them. We want to build a tree where we identify these goals. There might be states where we do not have any actions that we can take anymore. So, for example, when all the cards, the 5 cards are played, then there is no action anymore because I don't have any cards left. So these are then called the leaves of the tree. And the last notion we need is the depth of the tree. So you start with the level 0. So basically the depth of the node is the distance from the root. So this is the vocabulary that we need when we now talk about these trees. Search can also create roots, which would be then cycles in those, but we try to avoid them, and I'm going to talk about this later. So basically, if you have such a state space representation as we have here, we want to find a solution through search. And any of those starting points with a Hoover could be the initial of our search. We could say we want to start in the position left up, and that would then be the root of our tree. And we would then put this situation, right? So let's call it the state number 1. So we start with state number 1. And now, what are the options that I have? Is just build up from the state space a tree by just enumerating all the possible options you have from this state. So let's call this 1, 2, 3, 4, 5, 6, 7, 8, just for simplicity. And what are now the options that I have to go from state number 1, which is the left one, top left one, to somewhere. It's very simple, very similar to what we just did. Yes, we can get to 2 and to 3. Which are the actions that you have to take to get from 1 to 2? Which action do I have to take to get from this top state to the one on the right from your side? Move right. And what do I have to take from number 1 to number 3 down here? I have to clean. So suck. Yeah? And there's one that we've forgotten, that we haven't mentioned, and that is the one that is, if you move to the left, you basically go to state 1 again. And that is one thing you often want to avoid. but it's not so easy to avoid that you go to the same state again. So this is one thing we have to take care of and look into more detail later. So from state number 2, that is the one on the right side, what are the possibilities we have? What are the actions we can take? We can suck, and then we get to what I call 1, 2, 3, 4, 5, 6. We can go to the left, and then we go to 1 again, and we can suck, and we go to, so this is incorrect, so this is suck, and we can go to the right, and nothing happens. Yeah? And then we can systematically build this up as far as we want. And then you see here, this is exactly what we just did with the Schnapsen as well. And this is the pseudocode algorithm that you have doing that. You initialize your search tree to the initial state of the problem. So this was where we start, the situation we want to start with. And then we loop through all the possible candidates of paths that we can go, or decisions that we can take, or the actions that we can take. There's even an animation. So if we think about again this traveling from Arad to Bucharest on a travel, then we just have to build this tree by looking at all the possible ways that you can take from one of the cities to the next one. So you choose the next nodes from your tree. If you haven't found, if you can't find any other node, then you fail. If you can expand, then you add these to your data structure, to your tree. So now I added Sibiu, Timisoara, and Zerend to the data structure. And then I do again. I choose one of the nodes. So in this case, I would, for example, choose Sibiu. And I expand again. And here is the point that I choose some kind of node in which to further expand the options. And this determines how I search through the tree. So we look at 2 of these algorithms in a minute, or one of them before the break and the other 2 after the break. Because this is sort of the basic algorithm that helps us to solve all of these problems systematically. First, I want to repeat what I said before and make it explicit here that there is a clear distinction that you need to understand between the representation of the problems themselves. So that was the Hoover and the mathematical representation of the jogs and so forth, and the data structure in which you implement your search, so the search tree. And then you can, in this data structure, you have the nodes in your structure, and you define the notion of a child, you define the notion of a path, the father or the root, and so forth. This is all in the data structure, whereas the state representation is really the views of the world with the transitions that you can take from one state of the world to another one. So we're still on the problem side. So we're looking into some of these search strategies now, and today we look into the uninformed ones, where we just take a systematic view through all the possible nodes in the tree in a systematic way, without having some heuristic values or some understanding about what is this search about. That is going to happen next Tuesday. So today I want you to understand breadth first search, depth first search, depth first limited search, iterative deepening, and then look at some of the other properties of this search. So here is the pseudocode version of this tree generation algorithm. What you do is that we have a notion of a fringe. That is a very important notion here, and that is a data structure that contains the nodes that still have to be expanded. So we somehow store those nodes in a list or in a, and the way we store those nodes help us to determine the search. That comes in a minute. So we have this list of nodes that we want to expand, and we put the root of our search, our initial state into this fringe, and then we loop in an algorithm. So if the fringe is empty, then we don't have any nodes that we can explore, and then we're done. And we're done with a failure if we haven't found the solution before. That's the first line of the loop. Let me see whether there's some highlighting. No, it isn't. So that's the first line of the code, is if there is nothing in the fringe to be explored, then stop. Otherwise, take the first element from the fringe. If it is a solution, then you can stop. And then you return the solution, which is the node and the path to the node. And otherwise, you expand all the children from all the options that you can reach from this first node in the fringe and add it to the fringe in some way. And this is this notion of expand. And we are going to look into several examples later of how you do this expansion and how to apply this algorithm so that it is clear why this way of adding nodes to the fringe gives you different search strategies. And that's what we're going to do in the second half. So let's have a break now of 15 minutes. Let's start at 12 it is.